Radioactivity is not a byproduct of civilization or modern technology. It has always existed since the beginning of the universe. We learned about radioactivity when Henry Becquerel unexpectedly found that uranium salts could expose photographic plates even if they were securely protected from visible light. After Becquerel's discovery, Marie Curie found that radiation oddly transforms uranium into different elements. What exactly is radioactivity? It is a process that makes an unstable nucleus more stable. To be more stable, the radioactive nucleus either emits a particle or just emits energy. This procedure might create a whole new element from an existing one. Radioactive decay occurs randomly. It appears that there is no rule. There are nuclei that decay instantly, those that take a while to decay, and those whose decay cannot be awaited. However, the rule becomes evident when there are a lot of radioactive nuclei, or radionuclides for short. The time required for half of the nuclei to decay for each radionuclide was determined to be specific and constant. This period, referred to as the half-life, is an essential quantity for every radionuclide. The number of unstable nuclei, represented here by the letter N0, halved and decreased to half of the original amount when the first half-life expired. Once again, after the second half-life period ended, the initial number of unstable nuclei halved. However, this time the initial number of unstable nuclei was half of N0. The remaining number of unstable nuclei fell to a quarter of N0. This process continues indefinitely, with the original number of unstable nuclei being halved at the end of each half-life period. Adding a little bit of math to this entire scenario would be wise now. Each development process, which is dependent on the original state, is based on a specific natural number E, which has a value of around 2.72, the so-called Euler's number. Assume you have deposited $100 at a bank and are paid 100% annual interest rate on that amount. After a year, you would have $200. However, if interest is calculated and attributed to the principal twice a year, you will have $150 in your account after the first 6 months, because you were credited with half of the interest, but at the end of the year, the sum in your account will increase to $225, because the interest in the second half of the year was calculated on the basis of $150 rather than $100. If the year is divided into n parts, where n is a large integer, and interest is applied to the principal at the end of each period, you will have slightly less than $272 in your account at the end of the year. Thus, at 100% annual interest rate, the maximum amount of money that may accumulate in your account in 1 year would be nearly 2.72 times greater than the amount you invested. The mathematical formula that describes this type of growth is S equals U times e to the power of k times x. Here capital S represents the accumulated amount of money, capital U denotes the invested amount, lowercase k signifies the interest rate, and x indicates the number of years the money is kept in the bank. Your account balance grows exponentially. as does the mass of a growing tree or the number of mice in the population. The same logic applies to radioactive decay, where the number of unstable nuclei falls over time, as indicated in the negative exponent minus lambda. The number of unstable nuclei n after time t depends on the initial number of unstable nuclei n0 and the decay constant lambda, which is unique to each radionuclide. Lambda indicates the probability of decay of a single nucleus in the time unit. If the initial number of nuclei is cut in half, the elapsed time equals one half-life. By crossing n0 and applying logarithms on both sides, the relationship between the decay constant lambda and the half-life may be obtained. The total number of unstable nuclei at any given time can now be expressed as a function of the radionuclide's half-life. Another quantity that is quite significant is the activity. It provides us with the number of radioactive decays that take place in a piece of radioactive material every second. Activity is unique to a given sample, as opposed to the half-life, which is a feature of radionuclide. The product of the number of unstable nuclei and the decay constant lambda can be used to indicate the material's activity. The number of unstable nuclei multiplied by probability lambda yields the expected number of nuclei which will probably decay in the next second. By adding the previously found expression for the number of unstable nuclei into the formula, the final equation for the activity, which is measured in becquerel, can be obtained. 1 becquerel is equivalent to 1 radioactive decay per second, and A0 is the material's initial activity. For the simple fact that it contains more radioactive nuclei than a smaller piece, a larger piece of the same radionuclide will show more activity than the smaller piece. Consequently, rather than defining the activity at the sample level, it is important to do so at the level of radionuclides. A specific activity is obtained by dividing the observed activity by the mass of the sample. This activity is denoted by a lowercase letter a and is stated in units of measurement of becquerel per kilogram. The observed average values of the activities of many things from daily life, including ourselves, show that radioactivity is not a creation of modern science. We are exposed to radiation every day, from natural Earth sources in addition to cosmic radiation, which, as the name implies, emanates from space. The map shows a wide distribution of extremely hazardous radioactive radon gas indoors throughout Europe. Many more radionuclides, including thorium and uranium, also contribute to the Earth's background radiation. In any case, millions of years of exposure to natural radiation has enabled us to adapt. What is disturbing and can pose serious long-term issues is the uncontrolled and underregulated use of radionuclides in medicine and industry.